Hi everybody, welcome back. We are continuing with our Chapter 12 notes, and this is, I'm glad to say, our last chapter, and we're hopefully going to finish it up soon. So we're going to continue with our second section. This is the beginning of our section 2, starting with gravity due to a sphere. The note slide that says gravity due to a sphere, right here. And this is simply pointing out that the fact that anything that is spherical in its shape and also has its mass spherically distributed. What this means is that the mass is distributed all around a central point evenly. It doesn't have to be uniformly distributed. And I'll explain what that means in just a second, but it needs to be spherically distributed. Here's what I mean. If we take, let's draw the Earth right here. Okay, there's the Earth. Well, we know that the Earth's core is fairly dense, okay, and the outer parts of the Earth are fairly light. Well, we can say that that's not uniformly distributed. After all, it's not the same mass all throughout. Much of the mass is at the center, and less of it is towards the edges. But it is spherically distributed. That is, all the mass is distributed around a central point. So what that means is we can think of the Earth as a point mass. All of its mass existing at one single point somewhere in the middle of the Earth. You can do the same thing with say, I don't know, a balloon, a toy balloon that you might blow up. Okay, now they're certainly not spherical. Just pretend that they are, and they probably have a little tie thing at the bottom as well. But for the most part, they're spherical. But the point here is that all the mass is at the edges, right? All around here is where all the mass of the balloon is. And there's basically nothing in the middle right here. Well, that's fine. It's still spherically distributed, even though it's not uniformly distributed. That is, the mass is on the outside, no mass on the inside. That's fine, as long as this is distributed spherically. So this also can be thought of as a single point mass. That's supposed to be an X right there. A single point mass. This balloon having gravity originating somewhere in the center right there. So that's the point here. Gravity due to a sphere can be thought of as a single point mass. Okay, moving on. This diagram right here just points out a very famous experiment by a scientist named Henry Cavendish, where he actually measures or gets very, very, very close to the actual value of G. 6.67 times 10 to the negative 11th, our gravitation constant. It was kind of a neat apparatus. He had two sets of masses, and these smaller masses you can see are separated, or they're on the end of a rod. And the gravitational attraction between these masses here made the rod, which is on the end of this string or this thread, made it spin, and because of that spin he was able to measure how much gravitational attraction there is. That's a very simplified version of it, but it was done actually with an apparatus that you could house in your in a room. It was a fairly large apparatus, but it was called the Cavendish experiment. What he was really trying to do was weigh the Earth, but he really wound up coming up with our value for G. All right. So he was weighing. He was trying to weigh the Earth, but found this gravitational constant G that relates force and mass and radius or distance between two objects that have mass. Before this, measuring G, that is our 9.81, Earth's G Earth, being 9.81 meters per second squared, we measured that directly, or we measured it, you might say, empirically. That is, actually dropping something and seeing how far it goes in a certain amount of time, and coming up with an acceleration for that. Believe it or not, the radius of the Earth was also measured directly as well, using geometry and trig. But Henry Cavendish enabled us to actually do it mathematically. So we're going to calculate the mass of the Earth based on Henry Cavendish's calculation of G. Okay, so let's find the mass of the Earth. What is the mass of the Earth? Well, let's write a few things down. We know that the force caused by gravity is equal to mg. I think we all agree with that. Or force is equal to ma, or in this case, our acceleration a is gravity g. And we also know from this chapter that the force that we feel as gravity is the gravitational constant times one mass times the other mass, and I'm writing this instead of an m1 and an m2, I'm writing it as a small m and a big M, like the mass of U versus the mass of the Earth. All this divided by r squared. Okay, that should look familiar. Well, again, if these two forces are the same force, if they're equal, we can set these other equations equal to each other. So we can say that the small mass, whether it's a bowling ball or a person or whatever, times gravity equals the gravitational constant times the small mass times the large mass, and that is the mass of the Earth, which is pulling on us, divided by r squared. Okay, well, we can see right here that a few things are going to, well, one thing is going to cancel out, and that's our small mass. It doesn't matter what that is, as a matter of fact. So we can say that gravity, or the acceleration of gravity on Earth, or any planet for that matter, is our gravitational constant times the mass of that large body divided by the radius of that large body. Okay, so this is going to be, and in fact, we're going to revisit this a little bit later on. This is going to be an integral equation for us. It's based off of these other two equations right here that we knew from before. Okay, well, if we know then the gravity of the that is the acceleration of gravity of the Earth, and we know the Earth's radius, and we know what g is, we should be able to solve for the mass of the Earth. So let's go ahead and do that. Let's first rearrange this to solve for mass. I'm going to do it. I'll do it over here. I've got some space. Mass of the Earth. I should put a little e there. Or the capital M should indicate that that's the Earth, or the very large object. Would be equal to, let's see, we'll bring the r up and the g down, r squared times g divided by, that is, this is our acceleration g, divided by our gravitational constant, capital G. Now you probably have this r stored in your calculator. That would be the radius of the Earth, right? The radius of the Earth squared times small g, well, we know what that is, we basically know that by heart, divided by capital G. And if these are plugged into your calculator, that is the radius of the Earth and g, you should be able to calculate it fairly easily. So in my calculator, it would be r squared. I'm going to just say times 9.81 divided by g. Again, you can call radius of the Earth whatever you want. I happen to call it r, so that's why I'm writing it like that. Which means that comes out to the mass of the Earth. That should be a capital M, sorry. I have is 5.99 times 10 to the 24th kilograms. Okay. And just for future reference, let's convert this to grams as well. And I'll show you why in just a second. 1 kilogram equals 1,000 grams, right? So that means we would add 3 more 10s or 3 more zeros onto that that exponent there. So that would be 5.99 times 10 to the 27th grams. All right, and that's pretty darn close to the value that we have for the mass of the Earth. I think our official value is 5.98. I think I rounded a little bit differently. Okay, so we have the mass of the Earth based on or solved using the gravitational constant g.